be working. Hello everybody, my name is Michael Eickenberg. I work in the parietal team of INRIA, which is in Saclay at Neurospin in the CEA. I work generally on brains. I do predictive modeling on brain data. But today I've come to present a little software package that I've been working on with a friend at Montreal. So the title of the talk that I sent in was sklearn-theano, easy and powerful feature extraction for your scikit-learn pipeline. Since we will be having a lot to do with these nice animals that you see on the left and the right, we are going to change this to a simple method for the detection and localization of Bradypus variegatus. I have an asterisk up there. No animals were harmed. The other two asterisks is that these slides are heavily inspired by Kyle Kastner's talk, who is the person that I made this with, at EuroSci-Pi 2014, with the additions that were necessary. But great thanks to Kyle, because these slides, well, they turned out to be at least a little bit of fun. So, the plan is to find these. This is a sloth. It's a three-toed sloth. To classify them, find them in the wild, localize them exactly, do something in between, make diagrams, make a business model, create a startup, and make money. So what I'm going to present up to here is classification and location, and the business model and the startup is homework, if you feel like doing it. So I'm going to introduce a little bit the feed-forward architecture of certain neural nets. I will be using introductory slides that you have probably seen a lot. I will still do this to have everybody on the same page. The example will be computer vision and how things have changed in the last few years and rapidly. So, before 2012, and you've probably seen this once again, the pipeline for object detection looked something like this. The image goes into a pipeline that consists roughly of three big units. The first unit is feature extractors, roughly biologically inspired, which means that they do kind of edge detection. You have Sift, Hog, Surf, there's Daisy, there's quite a few other ones. But they all with more or less nice properties for detecting edges or interest points. This goes into a feature aggregation module, which basically models the structure of the distribution of these key points, because they do still live in a high-dimensional space. So we do some sparse coding or clustering in order to get a grip on this distribution. And based on that, we have hopefully a linearization of the problem. Is this object there or not? That is how it looked before 2012. Every one of these stages except the last one, well, the middle one is unsupervised learning. Certainly the first one is handcrafted, and we have three building blocks stuck together. What we see nowadays is this. We have a neural net doing trainable feature extractors, we have a neural net doing trainable mid-level features, and we have a neural net doing classification. This is just one big neural net with many layers. What we didn't picture here is, you see it at the top right, big GPUs or CPU clusters, as mentioned in the talk before, and 1.2 terabytes of images. Now this is a big difference. We need to be able to process that in order to get a nice representation through a huge neural network. Packages in order to do this, non-exhaustive. There's Theano, which I'll be talking about. a little bit. PyLearn2, which is based on Theano for neural networks. Caffe, which is probably something like becoming the reference for standard implementations of feed-forward neural networks and convolutional networks. There's Torch, which is probably at kind of the same status, which is based on Lua. Then we have a few interesting Python packages for making neural nets, such as Blocks, coming from Montreal, and Lasagne, which has been started something like August last year by Sander Dielman in Belgium and other people. And there is a huge activity on GitHub. It's worth keeping an eye on this package. It'll become something very interesting. So, the last introductory slide, just to get everybody on the same page here. We have a lot of things that many people have seen before. We have a convolutional architecture here, which means we have a filter that moves over an image. People love showing their filters. Like many papers up until maybe last year loved showing their filters. These are real first level filters that act on the image for edge detection or color texture boundary stuff. What you see in the other two panels are actually deconv net representations of higher level layers of a neural network, just to see what they're interested in an image. So you have the second layer that is interested in more complex features than the first layer, and the third layer in even more complex features. You can also see at the bottom, the feature extraction classification has become basically one. That's it for the introduction. So now, sklearn-theano. What did we make it for? Well, to detect him, to detect that, and to localize him. But before we talk about scikit-learn-theano, let's talk about scikit-learn and Theano. So we have scikit-learn here on the left, just a few specifications. Scikit-learn exists since 2010, if I'm not mistaken. It was basically taken as a Google Summer of Code project and turned into the biggest machine learning package there is by our team, INRIA Parietal, and now there are a ton of collaborators all over the world working on this machine learning library. It's very fast and it's very flat, which means that if you look at the code, you can find the functionality really fast, and you can actually start coding and understanding this pretty quickly and don't have to look through 8 layers of classes in order to find some code. It's written in Python, and pip install scikit-learn if you don't have it yet. Theano, on the other hand, is also a scikit-learn, is also a Python package. It is a compiler for mathematical expressions. So, if you're familiar with NumPy, which is basically the core numeric engine of Python, for Theano, you just write NumPy expressions and concatenate them as much as you want, and it will compile them for you. And another extra cool thing is automatic differentiation. So the expression that you put in, if it's not too violent, can be differentiated. So you have the derivative. Now the question, like, what is a neural network if it's not a concatenation of mathematical expressions? And what is backprop if it's not a way of calculating the derivative, which is actually the way that Theano is doing it. You switch between CPU and GPU in one flag. Sometimes you have to do some extra considerations, but that's basically it. Just to show you how this in general works in scikit-learn, this is enough code to do some simple classification. So in these first few lines, I just import a scalar for the data. The data that comes in basically gets its mean removed and gets standardized. Second line imports a principal component analysis. And the third line, a logistic regression. The fourth line is something in order to stick these together and make a pipeline. So look at this very closely. I'm making a pipeline of the scalar, a PCA that whitens the data and keeps 10 components, and a logistic regression. I can fit the pipeline on training data, training data plus labels, and I can predict on test data and get out maybe some predictive labels. This is the basic way that we work with scikit-learn. The interesting thing here is, the question is, could we put images into this? And right now, we would like basically to put the sloth image into this pipeline and be able to detect the sloth. The thing is just that a standard scaler and a PCA are just not going to make us able to detect the sloth. They're just, anything in scikit-learn right now is not powerful enough to detect the sloth. We want to put a preprocessor in the pipeline here, such that the logistic regression just does a linear classification and finds our sloth. A very quick introduction to Theano. We have an import of Theano. We have an import of the core module, which is tensor. And we need some random numbers here. I defined some shapes of matrices and vectors. I made these matrices and vectors as Theano, what is called shared variables. I filled them with random values, W1, B1 until W3, B3. Here, in net, I make one of these mathematical expressions that I talked about. The mathematical expression is, I take the input, I make a dot product of the first weight matrix of this input, I add a bias, I take the rectifier linear unit of that, I multiply it with another matrix, add another bias, take another rectifier linear unit of that, multiply it with another matrix, add another bias, take a softmax, and have an expression. Now, if anybody looked closely at these shapes, I don't know, who knows what data set I'm interested in working on? I heard it, MNIST, exactly. 728 is 28 squared, which is the number of pixels that you have in MNIST, 28 by 28. The output is going to be a 10 vector indicating whether it's going to be a number between 0 and 9. So this would be a network that classifies an MNIST digit completely wrongly because I initialized it randomly. There we are. Now, sklearn-theano, a package written by Kyle Kastner, who is now doing grad studies at Montreal, and myself. We were both interested in this. I needed it for working on brains. He was taking part in a Kaggle competition to detect cats and dogs, and needed the power of the network called Overfeed by Pierre Salmanet. We wanted this to be an easy interface to train networks that we can plug into scikit-learn. This is the main goal here, and we'll see some examples. So this, you can see, localizes a cat and a dog. The pipeline that we're now working with is sloth, goes into a trained feature extractor, which can, for example, be Overfeed or other pre-trained models. Then we use scikit-learn to have a little classifier and have an output. Again, not pictured, weeks and weeks of training of these feature extractors, which we leave to other people that are very good at this, and we use the pre-trained nets and make them available. So one of the nets that we're making available is Overfeed, which was contest winning in end of 2013, beginning of 2014. The architecture is here on the top right. It can detect white wolves very well, among other things. It had a very, very good error rate at the time on ImageNet. So what we do to be able to classify now is we make a pipeline with what we call Overfeed transformer or Overfeed classifier. First pipeline would be just Overfeed classifier if the concept that we're talking about is already one of the 1,000 ImageNet concepts. We just need Overfeed classifier, put the image in, it will tell us what it's seeing. More general purpose, using penultimate or even before layers of representation of the network, is the Overfeed transformer, which would take an image transform it until a certain layer of the neural net, let's say the third to last, which is the last convolutional layer, and then add a logistic regression on that, hoping that it has sufficiently linearized our problem. So this is the basic thing that we do with sklearn-theano. The weights are downloaded automatically whenever you want to use this. Sloth detection, as you see here on the right, works very well. Sloth localization, how does this actually work? If you look at the paper of Overfeed, they make it very explicit that sometimes images are bigger than the actual convolutional neural net receptive field. So here we have the convolutional neural net size, and it's going to move over the image. Now note that the last layers of the convolutional neural net are fully connected, but we can still turn them into a convolution over the whole image. And we just walk over the whole image, as you see in yellow there, very expressive this one, and see what the convolutional net sees. And here it basically sees sloth in all these yellow points. I admit that there's a hole here in the middle, and when we inspected that, it said carpet. Which is not completely surprising because the kernel is that big, and if you put it here, then it will basically see some sort of texture that has something similarity with carpets. What we then do is basically put a bounding box around that, and we've localized the animal. You can find this in a tutorial that I put up on the webpage. We also have generative adversarial nets, or basically the nets that were made by Ian Goodfellow. I do not have animated GIFs here, which would be really cool, but we can basically generate, we have a neural network that generates samples that look like samples from the data set, from pure noise. So you put in pure noise into this thing, and it will generate a sample, like a digit, a little C4 image, or a Toronto face. The way it does this is by a min-max two network problem. One network tries to generate from noise images, and another network basically tries to learn to classify whether an image was generated by the first network or it was a real image. And the first one, the generator, tries to fool the second one, and the second one tries to figure it out. And this gives rise to really, really nice representations. There were follow-up papers on this, very interesting. As of this evening, and I'm proud to announce it, scikit-learn-theano also features GoogleNet. GoogleNet is another contest-winning, huge neural network. This is the architecture. If you count these blobs, you have around about 100. They consist of these inception units. If you count the inception units, there are less. It was made at Google, and it was made available or trained by the makers of or people that are working on Caffe. We were able to get this architecture, so I merged it, yeah. I merged it, I was happy about it, in time for the deep learning meetup. So we actually managed to get Berkeley Vision GoogleNet into Theano, into sklearn-theano. Now, knowing that Caffe also has a Python interface and a MATLAB interface, you may ask yourself, so why did we do this? We have two reasons. We want to make it really easy to use these in scikit-learn. And the other side effect that we have created by this is that now this Caffe GoogleNet, this huge architecture, is available as Theano expressions. So anybody using Theano can now build on this pre-trained model, fine-tune it, do whatever they want with it, if you are a person that prefers working with Theano. So we have these two advantages. For many, many things, Caffe is a great library. Please go and check it out. Takeaways: scikit-learn if you don't know it, check it out. Theano is a Python package to do to make mathematical expressions, thus also neural nets. Neural networks are great feature extractors that can find slots. You can use these large neural networks with sklearn-theano in scikit-learn pipelines or as building blocks for your own Theano network. Future work, bring more of these pre-trained networks in. For example, also support audio and text. Enable better fine-tuning to specific tasks. If any of you are interested, please send us a PR or help us. That would be really great. And another thing that I'm really interested in getting this, I've already got a little pull request up, is the scattering transform developed at the UNSU. That's it. Thanks very much. The code is up here. We've got some Twitter and GitHub handles here if you're interested in following. Thanks very much. Question?
Any questions?
Yes. Yes.
So basically, how does it work to use a model trained with Caffe into sklearn-theano? Is it like an automatic procedure, or do I need to make some fine tuning or some manual like definition of the model or something?
I'm really sorry, could you repeat the beginning?
Yeah, so I have some models that are trained with Caffe, and I want to use them with sklearn-theano, for example. So do I need to do any manual operation to translate the networks, or is it fully automatic so far?
So, as of now, it needs a little bit of manual tweaking for a very simple reason. What we are doing is we take the proto-buffer file that defines a Caffe net, and we parse it and create the Theano expression, make the function, and then you have to test it a little bit. Usually, it just like for GoogleNet, it took me a while to actually get the convolutions aligned and get everything run properly. All the units that are used in GoogleNet work fine, but not 100% of all the Caffe processing units are implemented. Otherwise, the parser reads your file, no problem. It creates the units, no problem. And basically, all you have to add is, okay, Theano, compile this function, and you would have it.
Okay. And how about the weights that are trained and stored like in the Caffe model file? Can I also read them automatically?
The weights that are stored in your binary Caffe model?
Yes.
Yes, this is the exact way how we proceed for getting Google.
Thank you.
Can you tell us a bit about the speed?
Thanks very much for this question. So right now this this network is, well, we made it such that it works definitely on CPU for people who have not used a GPU yet. The speed for running for feed forwarding a test image on GoogleNet on CPU was 2 seconds, which is basically really horrible compared to a GPU. This is an image of 224 by 224. The PyCafe actually took a little bit longer. So there are a few implementation details that need to be taken into account before we make sure that GPU actually brings a big speed up. Right now we can switch to GPU, but some of the functions such as max pooling are not perfectly implemented for GPU. Yes?
I was wondering about the licensing issues. You're basically using some of the Caffe models as well as overfit, I guess. And I'm wondering if someone at a company tries to find a slot of orange color, for instance, as opposed to the brown ones that you have. Is it easy for a company to essentially use a scikit-learn and essentially train it on these type of things? Is there a licensing issue at all? Do you have any views on that?
So, I don't, so the thing is, ImageNet on which this is trained is afflicted with copyright problems. Like there are many images that have. So if you use this, I think the term is that you should only use it academically. I think I'm not completely sure, but ImageNet has terms. Now, the pre-trained weights are derived models from ImageNet. What we did in scikit-learn-theano is provide downloaders for these weights and refer to the licenses of the people that are using them, that created this. So from our point of view, it's basically use at your own risk. However, like use at the license of the people that created this. However, I know little about this, but I have the feeling that it is still not entirely clear how to treat this ImageNet issue.
Okay, so it's just the beginning.
Yeah.
Okay. Thanks.
Yes.
Just to add on the licensing issues. So when you train your own network with overfit, it's commercial. With Cafe, it's open source. So if you input a train network on another data set, different from ImageNet, that was trained with overfit, you will still keep the copyright of the overfit code. Is overfit training available? I don't think so. Yes.
It's available? Code for training overfit? I don't think it's available.
It was at some point in the beginning of overfit.
Okay, then I'm not sure how to answer this. Like when we made this overfeed wrapper, the training procedure was not public, and we never looked back. But it was like, okay, we might make this public sometime, but we didn't wait for that. So
okay. For Cafe, there is sure there aren't many problems. It's open source.
Yeah.
So just to clarify something, those are the licenses of the software project, and sklearn-theano doesn't use the code of those projects. So those licenses are not even impacting. But the licensing to use the models is different, and it's a gray area on the Berkeley website for Cafe. They say that ImageNet itself has some copyright restrictions, but derivative works shipped as weights for pretrained models, statistical derivatives. Nobody really knows, but from their point of view, they don't put any restriction to use them, but we don't know whether the original copyright owners on the original image have some kind of derivative copyrights on the trained models, but probably not, but it has never been tested in court. So, it's, but everybody does it. So everybody uses ImageNet to train models.
Thanks very much for the clarification. Yes.
As far as overfit is concerned, Facebook has released open source code on top of Torch to retrain the overfit architectures on top of ImageNet, of course. So this is not the official training code, but you have an open source example to run from the ground up a complete training for overfit. Yeah.
Okay.
Thank you. One last question, maybe? No? Right. So thank you.